This experiment investigated the magnetic force and was done by Olivia, Marlon, and Gwyneth. The purpose of this experiment was to investigate how the strength of the magnetic force would change with distance. We also determined the magnetic force of an individual magnet, and then finally determined the relationship between the number of magnets in a stack and how that would affect the strength of the magnetic force.
The theory for this lab uses many concepts. One of the first concepts is that there is an inverse relationship between magnetic force and distance, which is shown and represented by the equation F equals 1 over d squared. This equation shows that as distance increases, the force will decrease, or as distance decreases, the force will increase. The second concept applies Newton's first and third law to the experiment. Newton's first law states that an object at rest will remain at rest until a force is exerted on it. When we apply this law to our lab, we can see that the weight force of the magnet is in equilibrium with the normal force exerted up from the scale. Newton's third law states that if object A exerts a force on object B, that this force will be equal and opposite to the force object B exerts on object A. This is an important detail that we can see when looking at the reading of the scale, as the reading on the scale is the normal force that is exerted by the scale on the magnet.
When a magnet is at rest on the scale, it exerts a constant weight force on the scale that points downward. The scale then exerts a normal force on the magnet that points upward. This normal force is the reading that is shown on the scale. When another magnet is brought closer towards the magnet at rest, a push or pull force is exerted by the moving magnet, which will affect the normal force of the scale on the object and thus change the reading of the scale. Two different situations were demonstrated in this lab. For an attractive scenario, the moving magnet exerts a pulling magnetic force on the magnet at rest. This will point in the same direction as the normal force and opposite of the weight force. As the moving magnet gets closer to the magnet at rest, the magnetic force will increase. Because the weight force does not change, as the magnetic force increases, the normal force decreases so that it will remain balanced with the weight force of the resting magnet. This is congruent with the decreasing number we read on the scale. This can be viewed mathematically with the equation in purple. For a repulsive scenario, the moving magnet exerts a pushing force on the magnet at rest that points in the same direction as the weight force that is pointing downward, and in the opposite direction of the normal force. As the moving magnet gets closer to the magnet at rest, the exerted magnetic force will increase. Again, because the weight force does not change, in order to keep the forces balanced, the normal force that points in the opposite direction increases, which can be seen by the increasing number we read on the scale. The equation in purple also summarizes this relationship.
The materials used in this experiment was an electronic scale, make sure that this is not magnetic, pole, a meter stick, magnets, make sure these magnets are stackable, tape, scissors, cardboard, and lastly, Excel. We began this experiment by making a cardboard case to wrap around the stack of magnets on the scale. We cut 4 strips of cardboard and then used packaging tape to tape those together to make a rectangular box, also making sure that we covered one of the open ends. This was so that we had a way to secure the magnets to the scale and allowed us to make measurements without fear of the magnets flying away.
We then set up a pole at the lab station and moved the electronic scale towards it so that the scale was as close as possible to the pole without touching it. A meter stick was then secured to the pole using tape, making sure that the 0 end mark was level with the scale. Next, we taped the cardboard box at the edge of the scale so that it was as close to the meter stick as possible. When taping, make sure that the tape is lightly secured so that it doesn't pull down and obscure the weight value. We then made note of the height of our cardboard box on the meter stick. We then took our stack of magnets and split them evenly into 2 stacks and put one of these stacks into the cardboard box, then measured the weight that appeared on the scale. We first measured the forces in the attractive situation, making sure that the opposite ends of the magnets pulled towards each other. We then took the second stack of magnets and held it at a height of 30 centimeters, which is 20 centimeters above the starting height of the magnet on the scale. From here, we began moving the magnet down, recording the weight that appeared on the scale every 1 centimeter. It was critical to make sure that both stacks of magnets were directly on top of each other. This same procedure was repeated for the repulsive case, this time making sure that the ends of the magnets were pushing away from each other. After this, we used Excel to convert our height values to meters and weight values to newtons. It is important to remember to put the true height values. When reviewing the data, we noticed that some of the heights had the same weight value. Because of this, we took the average of those heights so that we could report only one height for that same weight value. We then used the equations in the theory to solve for the magnetic force. For attractive situations, we did the weight force minus the normal force, which is equal to the magnetic force. And for the repulsive situations, we did the normal force minus the weight force equal to the magnetic force. Once we found the magnetic force values for each situation, we squared our height values and took the reciprocal of that number. These values were then plotted in a linear graph with the dependent variable as the height and the independent variable as the magnetic force. We also displayed the equations and R values. Next, we decided to also plot the data in the power graph in order to reinforce these relationships and back up our findings. Although the same variables were plotted on each axis, the original height values were used for this graph rather than the squared and inverted values. The second portion of the slab begins with the same setup, and we chose to only use the repulsive situation to demonstrate this relationship. We also picked a constant height of 12 centimeters to perform all measurements, which is 2 centimeters above the height of the magnet on the scale. We then took one individual magnet, held it at that constant height, and recorded the weight. We then repeated this procedure for a total of 20 trials, until we had added 20 magnets to that stack. On Excel, we then made the appropriate conversions and graphed the number of magnets versus the calculated magnetic force.
The purpose of this lab first investigated the relationship between distance and magnetic force and how there is an inverse relationship between magnetic force and distance. As distance decreases between two magnets, the magnetic force increases and vice versa. This relationship is shown by our linear graphs. As you can see, the R values for both the attractive and repulsive situations are close to 1. This signifies a strong correlation between our data. We also created power graphs for our data, and as you can see, our power graphs also demonstrate the inverse relationship represented by F equals 1 over d squared, since the magnetic force is related to distance by a power value of negative 2.1 in both cases. This negative power value shows a relationship of 1 over x squared.
The second portion of our project determined the magnetic force exerted by a single magnet and how this magnetic force would be affected as the number of magnets in the stack changed. From our graph, the slope value indicates the magnetic force of a single magnet and was 0.0909 newtons. We were also able to conclude that the relationship between the number of magnets in a stack and the magnetic force was a proportional relationship. As more magnets were added to our stack, the number on the scale would increase. Furthermore, our R value was close to 1, signifying that our data had a positive linear correlation. There are many possible sources of error in this experiment. When we were conducting the second portion of the lab, we noticed that when we got to a specific number of magnets, around about 15 in our stack, we saw the number on the scale start to plateau. There are two possible explanations for this. One of these explanations is that we did not have a scale that was sensitive enough. Our scale was only able to read to the 100th place. If we would have had a scale that was more sensitive, it is likely that our results would be more precise. Secondly, this concept of leakage on the horizontal can also explain that plateau. If you look at the figure here, we drew the magnetic field lines for our situation. We know that the magnetic field lines will always curve back from the North Pole to the South Pole. Because of this, there will be a certain point where there will be more energy on the horizontal component than on the vertical. This means that some energy is not going to be read by the scale because it is going horizontal rather than vertical. Another possible source of error is with the magnets. The magnets had to be stacked in a certain way to where they weren't easily torn apart. If they were easily torn apart, this could have skewed our data. And finally, systemic errors in our methods. What we mean by this is when we were measuring all our data, it was very critical that we held the magnet stacks directly on top of each other. But because these magnets were very strong and were not stronger than a magnetic force, it was sometimes very difficult the closer the magnets got to each other to make sure that they were held directly on top of each other.